going to use the, bless you, we're going to use the combined gas laws to go ahead and solve. I'm feeling this color today. So, Kaylin said it's V1, P1 over T1 equals V2, P2 over T2. I'm going to tell you that your problems are going to get a little more challenging today. So it might be in your best interest to start identifying each variable, because now we're going to do multi-step problems where you have to use two laws to solve one problem. Okay? So for example here, this is going to be my V1, my temperature, this is my T1, and here's my P1. I'm looking for my volume. Here is my T2, and here is my P2. So after that, it's just plug and chug, except I have one extra step I have to take. What's that? Convert what? Celsius to Kelvin. Must convert Celsius to Kelvin. Right, Jenny? Yeah. Okay. So I'm going to have 106 liters.
Speaking of milliliter of mercury, you know in yesterday's homework
It was just meters of mercury. It's supposed to be millimeters. I corrected it for the other class.
I think about it for a second if there's actually 70 like a meter.
No. So what is your new temperature in Kelvin for the first temperature? 45 plus 273. Very good. We don't know V2. Our P2 is going to be 780. And your T2 is 293. What do you end up with? I need 4 sig figs here. What do you end up with? Helios, you have your calculator? Yeah. What'd you get? Oh, okay.
After I typed all of those, I found out I didn't turn on my
Yeah. First step, turn on calculator. Very good.
Okay, you got 92.66.
92.66 what?
I got 92.66 as well.
All right, 92.66 liters. Don't forget, guys, you need to include your units on here. For? I don't know why.
What?
Because there was 4 on the temperature that was given. So it would be a minimum of 3, but because there was 4 given in the problem, they felt it necessary to carry it out that far. That's
Oh, okay.
what I
So
did.
we can just see the problem and then. Okay.
Yes, 92.66. All right. A gas was collected over 21.000 degrees Celsius water. After equalizing water levels, the volume was 325.0 mil. Give the volume of the dry gas at STP. The atmospheric pressure at the time of collection was 102.9 kPa. So, there's a lot of information on there. These are the types of problems you're going to start getting. The first thing asks, the overall question is saying, what's the volume of the gas at STP? Right?
Yeah.
What we need to find then is we have to solve for the pressure using Dalton's law of partial pressures and then plug that in to our combined gas law.
Wait, when you solve what first?
Dalton's law of partial pressures.
For what?
Because we need to find it, the volume at STP, which means that we're looking for V2 when our T2 is equal to 273 Kelvin and our P2 is equal to 101.3 kPa, right? So we're looking for V2 and we don't know what that is. So we're going to use V2 over P, or V2 P2 over T2 equals V1 P1 over T1. We know T1, right? They told you what that is. What's T1? 21 degrees Celsius, which is what Kelvin? So we have 294 Kelvin as our T1. Our V1, we know what that is too, right? 325 mils. What's your P1?
101.3.
We don't know what our P1 is. 101.3 is what P2 is. We don't know what P1 is because we have to find the pressure of the gas at that point after it's been collected.
But it says after equalizing water levels.
Right, and so that means that the total pressure is equal to atmospheric pressure. That's why they say that after the equalizes. So that means that you're going to have P atmosphere is equal to the pressure of the gas plus the pressure of the water at 21 degrees Celsius. What's the pressure of the water at 21 degrees Celsius? No, you don't know what it is. You've got to look in your book. So somebody look on page 13.2. Chapter in on the chart 13.2.
It's
It's page 325.
Yeah, 325, number table 13.2.
don't have the number quite on there.
You don't have 21 degrees Celsius?
No.
You have 20 and 25.
I'll give you 21. Yours is not as good. It's 18.650 millimeters of mercury. So what do I have to do first? I'm going to have to convert that to kPa. So 18.65 mmHg over 1. I know that it's 101.3 kPa and 760 millimeters of mercury. So go ahead and do your conversion.
What's your calculator?
There you are, madam. You're welcome.
2.485.
So I have 102.9 is equal to P gas plus what? What did you say the P water was, Zach?
Wait, why did you write 102.9?
Because it tells you that the atmospheric pressure at the time of collection was 102.9. The 18.65, that was the pressure of the water. So, but it was given in millimeters of mercury, so we had to convert that to kilopascals. So what did you get for 18.650?
I got 2.5 with using the, yeah.
2.5. So then we subtract 2.5.
Wait, how is it possible to
101.3 divided by 760 times 18.6.
Yeah, I got 2.5.
No,
So P gas is equal to 100.4 kPa. So that is now our P1. So now it just becomes a plug and chug. So you go back and we're going to set it up. So then we're going to take what we did, V1 P1 over T1 equals V2 P2 over T2. My V1, that's what they gave you in the original problem, so I have 325 mils. We just solved for your first pressure, which is 100.4 kPa. Our initial temperature, it told us it was 21, which is going to be, you already converted to 294 Kelvin, is equal to, we said our V2 is what we're looking for. Our P2 is standard, so that's 101.3 kPa, over our standard temperature, which is 273 Kelvin. Let me know when you got it. 299.1 is what I got as well. And that's 299.1 what? Milliliters. Very good. So did you understand why we had to do the Dalton's law of partial pressures first? Because they gave you, and you have to look at it and you have to say, what kind of variables do I have? How can I manipulate these numbers in order to answer the question?
Our P1 was the pressure of gas, right?
The P1 was the pressure of the gas. Yes, because that's what we're talking about. We want to, I don't care about the pressure of water at STP. We can look and find that in a chart, right? We want the pressure of this gas that you've collected. So let's review what we were talking about. What's Dalton's law of partial pressure? We just used it. Yep, what's the equation?
PXDM equals P gas plus P water.
Or we can have it another way, right?
Or it can be P total equals P1 plus P2 plus P3, da, 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 da.
Yep, plus all the P's you have. What was Boyle's law? What did that show us the relationship between?
Pressure and volume.
Pressure and volume. So was that inversely proportional or directly proportional? Inverse. It's the only one you've had that's been inversely proportional. So what's the equation for that?
P1 V1 equals P2 V2.
What about Charles' law? What did Charles' law give us the relationship between?
Pressure and temperature.
No, not pressure and temperature. Volume and temperature. So remember, that was V1 over T1 equals V2 over T2. Gay-Lussac's law, that was the one with pressure. Okay, and this is really cheesy, but I think that, like, the name Gay-Lussac, that's a lot of pressure to have a name like that, right? Especially back in those days. So it's the one with pressure and temperature. P1 over T1 equals P2 over T2.
But wasn't gay normally used to describe like
Happy?
Yeah.
You don't think it takes a lot of pressure to be expected to be happy all the time? I'd rather be gay by today's standard all the time than happy all the time. That's a little rough, don't you think? Gosh, I just can't do that. What's the combined gas law? Well, this puts all of these guys together. So it's V1, P1 over T1 equals V2, P2 over T2. It doesn't matter if you say P or V first. It's the same thing.
Instead of calling it the combined gas law, they should just combine all their names together.
The BCG law,
Yes.
I don't think that would fly at all. All right, so we're going to talk about a little bit about Gay-Lussac again. He said his experiment was known. He experimented with known volumes of gas, and he was able to summarize his experiments, and we now call it Gay-Lussac's law. You know that. So at a constant temperature and pressure, the volume of gaseous reactions and products can be expressed as the ratio of small whole numbers. Duh, we just did that. But then Avogadro came by, and Avogadro, do you remember Avogadro? Why do you guys know him?
The 2.06.
Not 2.06, what?
6.024.
Not 024, 6.022. Oh my goodness. You guys really don't know him. Have you met him before?
Have you?
I have a huge
Are you 7?
At breakfast.
Calm down.
All right, so Avogadro combined the ideas of Gay-Lussac's experiment and gas volumes with Dalton's original ideas of atomic theory. And what he came up with was that equal volume, I'm going to do this in white, I think. He said equal volumes of gases at the same temperature and pressure contain equal numbers of molecules. No matter what type of gas it is. So what we can say is that gas volume is directly proportional to the amount of gas a given temperature and pressure. So simply said, we can say if it's directly proportional as V increases, N increases. Remember, N meant the number of moles? So this gives us a new law. New law, new equation. It gives us Avogadro's law. And Avogadro expressed the relationship as V equals Kn.
That looks like.
It's actually,
Name sounds like avocado.
it's,
I said that like 2 seconds ago.
that is actually a picture of Avogadro right there on Avocado's number guacamole, and that's sold at Trader Joe's.
That's why I said I had breakfast.
So we say V is the volume.
Who puts guacamole in a can?
It does that because it's vacuum sealed, so it doesn't oxidize. K is equal to a constant and N is the amount of gas in moles.
Is that your notes?
Do what?
Is that your notes?
Mm-hmm. Did you find it on RenWeb? Yeah. I changed the background so it's easier for you to see. When your volume increases, the number of moles increase. So if we look at Avogadro's law, Avogadro said that the coefficients
How is it possible?
in a balanced equation can be equal to the number of moles or the number of volumes of a substance.
Wait, how is that possible? How do moles just magically appear?
Moles don't magically appear. If you have a mass of gas,
Right.
then clearly you have a mass. So you have grams of gas. Can you go from grams to moles? Yeah, you can.
Right.
It's just a simple conversion
But
factor.
let's-
But mole is just a quantity of something. So that's what he's saying, Zach, thinking of it in a different way. If I have a Tupperware container, it can hold a dozen donuts, or I could use it to hold a dozen cookies.
Right.
Okay? So I'm going to have an equal number no matter what. That's all it's saying.
But like, I'm thinking it as like, if you have, I don't know, 20 moles of hydrogen gas,
Mm-hmm.
and like, that's in one vacuum container, and then you transfer that hydrogen gas to like a larger vacuum container.
I still have 20 moles. That's all I had to start
Right.
with.
So then he's saying that the moles increase.
Cheryl, can we go back to time?
That means that I can increase, yes. As the volume increases, it can hold more moles, can it not?
Right.
That's what it's saying.
But the gas itself doesn't make more moles.
No, it doesn't say that it's making more moles.
Okay.
Which means as volume increases, the number of moles it can hold increases.
Okay.
So let's go ahead and review. So it tells us, let's review what the formation of water from hydrogen and oxygen gas. What's the equation for that? Well, I'd have H2 gas plus O2 gas equals H2O liquid. Now I got to balance it, so I put a 2 here and a 2 here, and we're good. So what that's saying is I can read this. What did this coefficient mean up until moles? So that's like saying I have 2 moles of gas, of hydrogen gas, plus 1 mole of oxygen gas to make 2 moles of water. Avogadro said that we can go ahead and, if it's at a constant temperature and pressure, we can read that not only as moles, but as a volume. So I could say I have 2 liters of hydrogen gas plus 1 liter of oxygen gas yields 2 liters of water. That's what that's saying. So-
is moles the measure of volume also?
No, mole is a measure of the amount of something. Volume would be liters or milliliters or one of the ones that we've already used.
Okay.
So Avogadro's number tells you that 1 mole of any substance has 6.022 times 10 to the 23rd molecules or atoms, right? So the volume occupied by 1 mole of a gas at STP, what's STP again? Well, what are the units? So at 273 Kelvin and 1 ATM, so the volume occupied by 1 mole of gas at 1 ATM and 273 Kelvin is known as the standard molar volume of a gas. And that is 22.4 liters.
I don't call it that way. Any gas.
Any gas at STP,
One mole.
That has
1 mole of it has a volume of 22.4 liters.
Why do they have the same? Do they have the same density at all?
We're ideal gases. Remember, we're assuming the postulates of the kinetic molecular theory are true. So that means that they're acting as an ideal gas. So the volumes are negligible. Remember, their individual masses are negligible. Their volumes are negligible. And so we can assume that at STP, any volume of a gas is 22.4 liters in 1 mole.
You mean he just assumed that?
It's actually true, yes.
I like the wheel.
So we now have a new conversion factor. So we know
That one is,
that 1 mole
one mole.
of a gas at STP has a volume of 22.4 liters. Or we can write it as a conversion factor. Okay? So let's practice doing a couple of problems here with this new conversion factor. It says, what volume does 0.0685 mole of a gas occupy at STP? How would you set that up? You take what you're given and put it over 1. What are you given? 0.0685 moles over 1. And I want to know the volume.
And then we do 1 mole on the bottom.
1 mole goes on the bottom. Very good. And 22.4 liters. How come I can use 22.4? Because it tells me it's a gas at STP. So what is the volume of the gas of that amount of gas at STP? 1.53 liters. Very good. How about the next one? It says, what quantity of a gas in moles is contained in 2.21 liters at STP? It's the same thing backwards. Remember, this is a conversion factor, so it doesn't matter how you write it. So I'm going to take what I'm given and put it over 1. I want my answer in moles. Well, I know that 1 mole has a volume of 22.4 liters. And what do you end up with? 0.0987 mole. So now we've got a new conversion factor. So that means that we can now read chemical equations and answer questions about volumes and now use it to apply it to our gas laws. What it means is we have gas stoichiometry. Yay.
Can we write this on our cards?
No. This is something you have to know. So remember the flow chart? Remember how up here we had up here, we're going to have ions or atoms or molecules of A. And we went to moles A. And down here, we had our grams A. And then we went to moles B. And then we had the same stuff up here, so ions. I'm just going to write ions B because it's easier. And then we had grams B down here. How do you go from grams to moles? Periodic table, I'm going to use my molar mass. How do I go from ions to moles? Avogadro's number. How do you go from moles to moles? Coefficient ratio. Now at STP, I can have volume A, and I can use my 22.4 liters per mole. And so volume B, and that would be 22.4 liters per mole. So now we can now add this to gas stoichiometry. We can take it a step further. Okay? Today's Thursday. Don't forget, we have a quiz tomorrow. It'll be on everything we've done, yeah. And I feel like, especially when it's something like this where you have a lot of equations and a lot of things to do, it's best to have like smaller quizzes instead of like 2 honking huge quizzes. No, because we're going to, about the first half of class tomorrow, yeah. Okay, so propane is a gas that So we say propane is a gas that is sometimes used as a fuel for cooking and heating. Find the complete combustion reaction of propane, and I give you the formula, C3H8. What will the volume be in liters of oxygen required for the complete combustion of 0.350 liters of propane? What will the volume of carbon dioxide produced in the reaction be? And assume that all volume measurements are made at the same temperature and pressure. So we're all at STP here, okay? Well, it's a combustion reaction. How do I write a combustion reaction? Well, I'm going to start with my hydrocarbon, C3H8 plus O2 yields CO2 plus H2O. Now, this is kind of a culmination of multiple things that we've done all year. So now what's the first thing I have to do? Balance the equation. So how do you want to do that? Put a 3 in front of my CO2, okay? What else?
3 in front of the oxygen and 4 in front of the...
4 in front of my hydrogen, and that gives me 10. So 3, a 5 in front of the O2. Remember, Zach, we always leave oxygen last. Yes, Gabby?
Is the water supposed to be gas?
Yes. If it were a liquid, it would put the fire out, wouldn't it?
Well, then why are they all gas?
Because are we doing gas laws? Okay, so now that I've got it balanced, the first question it asks, what will the volume in liters of oxygen required be for the combustion of 0.350 liters of propane? So now I just take what I'm given, 0.350 liters of C3H8, and I want to go from volume A to volume B, right?
So we have liters, right?
So we have liters.
So then we're going to do...
So I'm going to use my 22.4, so I'm going to 22.4 liters on the bottom in 1 mole. And now I need to go from moles A to moles B. How do I do that? Coefficient ratio. So I know that 1 mole of C3H8 uses 5 moles of oxygen. And then I know that 1 mole of O2 has 22.4 liters in it. So then you just go through and you do the math.
And you do that last one because it wants the answer in liters.
Because it wants the answer in liters, yes. Even though Jenny's like, well, they will just cancel each other out. Well, then you can't do that because then you're not actually converting one substance to another. And what did you end up with?
1.75.
I agree. You end up with 1.75 liters O2. The next question asks you, what will the volume of carbon dioxide produced be? So how do you solve that? It's the same thing. So now what I do is I'm going to start with still 0.350 liters of C3H8. I've got to go from liters to moles. I know that 22.4 liters in 1 mole. Now I have to go from moles A to moles B. Well, I know that 1 mole C3H8 gives me 3 moles of CO2. And I know that for every 1 mole CO2, I have 22.4 liters. Zach, tell me what you get.
So the stoichiometry that we learned in the third quarter is pretty much just this. It's not going to be anything hard.
1.05.
1.05 what? Liters what? CO2. Remember, you have to include your substance when you're doing stoichiometry.
We also doing naming in the third?
We didn't. So let's take a look here. The following reaction takes place at STP. Calcium carbonate decomposes at a high temperature to form carbon dioxide and calcium oxide. How many grams of calcium carbonate will I need to form 4.5 liters of carbon dioxide? So now what am I going to do? I have to look at it, make sure it's balanced. It's balanced. Okay, good.
You go from grams to liters,
I'm going from grams A to liters B.
which means you got
Or liters B to grams A, or A. So take what you're given and put it over 1. So I have 4.5 liters of carbon dioxide.
Wait, no, isn't it liters B?
That's liter. It doesn't matter. Liters A.
I mean,
I know that it's 22.4 liters in 1 mole of CO2. I know that for every 1 mole of CO2, I have 1 mole of calcium carbonate. And now I need to get it in grams. Well, then I know that 1 mole of CaCO3 has a mass of, what's the mass of CaCO3? Look on your periodic tables.
I'm just trying to show it.
Calcium is 40?
Yeah,
Is calcium 40 even?
Yeah, 100.09.
40.08.
Okay, 100.09, that's what I got to. And now you just multiply it through. Cyan, your homework is like this. That's not you, don't get excited, we still have another minute, I think. So what do you end up with? Zach, what's your answer?
I'm still typing.
Well, you weren't typing, you were just holding your pen in your mouth.
That's my way.
No, it's not. You can't type with your finger in on your pen in your mouth and the other one under your leg. I need to know that you know how to do this. 20 point what? 20.1, but oh wait, we've only got 2 sig figs here.
So 20
So 20 what?
grams.
Grams of what?
CaCO.
CaCO3.
It should be 20 dot.
We could be like that.
No,
equal to the
oh,
volume.
20 dot grams. Very good, Jenny. Or 2.0 times 10 to the 1.
We have to